Hello everyone. So in this lecture, I'm going to derive the linear momentum equation, again using the Reynolds transport theorem by setting B system to the momentum or mv, and then in the integral form, and then we are going to solve some examples. So I think we will solve about 4 examples to find the hydrostatic forces that are kind of applied to structures, okay, using this linear momentum equation in fluids. And after that, we will briefly talk about energy equation and then derive the Bernoulli equation again using the mechanical energy equation. And so this is how we're going to move forward. So let's get started with driving the linear momentum equation. So according to Newton's second law, we have Newton's second law. We have the time rate of, this is just F equals to ma, but I'm just gonna write it in terms of linear change of linear momentum. So instead of acceleration, I'm gonna write it as time rate of change of the linear momentum of the system equals to sum of external forces acting on the system. Okay, so the time rate of change of the linear momentum of the system equals to the sum of external forces acting on the system. Okay, so this is the Newton's second law, and momentum is defined as mass times velocity, right? Or instead of mass, for a small particle, I can just write it as the density times the volume of that small particle. Okay, so this is the mass of the small particle times velocity, and velocity I show it with v, and it's a vector as it has components in x, y, z direction. So this is the momentum, and then if I want to write the Newton's second law in terms of mathematical operations, so it's the time rate. So the time rate is what is the differential, is a derivative with respect to time of what of the momentum in the system, right? So if I want to write it for the whole system, it's gonna be the momentum of all the particles, so I can just integrate over the whole system. Okay, so just for one particle, it's gonna be the momentum is rho dv times v, right? So this is the momentum for one particle, and then I want to, so let me write it down this way. So I write it as rho, as first I write the velocity, so it's gonna be v times rho dv. Okay, so this is just for one particle, and then if I integrate this over the whole domain, I'm gonna get over the whole system. This is gonna, I need to integrate it, right? So imagine these are small particles, all of these are small particles, and then you have the whole system, which is consists of these all small particles. So you need to integrate over the whole system to get these momentum of the whole system, okay? So this is the Newton's second law. This is the left hand side. The Newton's second law states that this equals to the sum of the forces that act on the system. So I just write the subscript sys, so F system. Okay, so this is just a simple Newton's second law, and again, this is the from your physics. This is just sigma F equals to ma, right? So this is just the more formal representation of that in terms of the linear momentum, and for all the particles that are in the system. Okay, so this is just recall this similarity. Okay. So now I want to use Reynolds transport theorem. So we want to use Reynolds transport theorem, and we want to set the B system in that theorem to mv, right? So if you remember, in the Reynolds transport theorem, B system is defined as what? Let me see if I have it. B system is defined as m times b, right? Small m times b. And now I have set b to small b to v, right? So this is going to give me the momentum, right? mv is what is the definition of momentum, right? This is how we define momentum. Okay, so this is going to give me momentum, and this equals to mb, which is the definition of B system, right? So as you see, we have set b, small b, to v, right? So now that we have this, I can put this into the Reynolds transport theorem. So so this is the Reynolds transport theorem. So let me see. These are all the terms. So this is the first term of that. And then just I need to substitute all the relevant terms, right? So I'm going to do it here. This is just a reminder for us that we had from previous lecture. So instead of B system, I'm just going to put substitute that with mv. Okay, so let's see what we are going to have. So we have d over dt of what? So instead of this, instead of m, I'm gonna again use this formula here. So this equals to mv equals to, if I integrate over the whole system, I'm gonna get v rho dv, right? So I'm just gonna write that down. So it's gonna be the integral over the whole system of what? Of v rho dv equals to the first term, which is this one. It's going to be partial derivative of time with respect to time over the whole CV of rho B. So instead of B, I need to write B, I need to write V, right? The velocity vector here, right? So I just write it down, V rho dV. And then we have the second term, which is the integral over the control surface. So let me see if I can copy that too. So now we have the integral over the control surface of V rho V dot N dA. Okay? So this is going to be the Reynolds transport theorem that we used. And substitute momentum in B system. Okay, so again, this is the linear momentum of the CV. This term is linear momentum of the control volume, the considered control volume. And this term is going to be the linear momentum flow through the control surface. Okay. So this is how Reynolds transport theorem helps us to get the linear momentum equation. So for a fixed CV, we can write the linear momentum equation as follows. So for a fixed CV, this term we know from here, based on the Newton's second law, equals to the sum of the forces. So I'm going to write it on the right hand side. So I will start from the from these terms. So we can get the derivative with respect to time, partial derivative with respect to time of the linear momentum of the CV, which is going to be the integral of V rho dV plus the linear momentum flow through the control surface, which is going to be the integral of over the control surface of V rho V dot N dA equals to what? Equals to the sum of the total forces that act on external forces that act on the system, right? So it's going to be sigma F contents of the coincident CV. Okay, so this is the linear momentum equation that we are going to use to find the forces that act on a control volume, a fixed control volume. Okay, this is how we are going to use that. So I'm going to solve some examples of that, so you will see simpler forms of this equation in a moment. So this is important equation that you need to remember. Linear linear momentum equation. Okay, so what we did was very simple. We just used the second law of Newton, and then also use Reynolds transport theorem and set B system to momentum, or mv, and then we were able to derive the linear momentum equation. Okay, so now let's solve one example of this to see how we can apply and use this linear momentum equation in fluid problems. Okay, so let's solve an example. So example. So the example states, determine the anchoring force needed to hold the vane stationary if gravity and viscous effects are negligible. Okay? So this is a vane that we have, and then the other given information in the problem is the initial velocity of the nozzle, which is 10 meters per second. So we have a nozzle here that shoots the water or any fluid into this vane, and then the water is kind of changes its direction because of the shape of the vane. And so the question is, what are the anchoring forces that are needed to kind of keep this vane stationary? Okay, so we need to calculate the forces that act on this vane by this fluid. Okay, so let's get started. We need to use linear momentum equation. Okay, so I want to show you how you should approach this kind of problems. Okay, and how you should use this linear momentum equation. As you see here, we have a CV, a control volume, control surface, and also the sum of the forces that are coincident, that are contents of the coincident CV. Okay, so let's see how we should use this. So as you may guess, we first need to define a control volume for this problem. Okay, so this is the first thing that we need to do. So we select a fixed CV, a fixed control volume in space. Okay, a CV, a fixed CV that includes the vane and a portion of water. Why it should include the vane? The reason is because we want to calculate the forces on the vane, right? So we need to, the CV needs to also have that and include that. So let me redraw the problem here again. So here we have this kind of vane. And then we have some water over that. So we have some water that is going water and any other fluid that is going here. We know the velocity at here, which is the velocity of the nozzle, is V1, but we don't know the velocity here, which I show as V2. The angle is theta. This angle is theta. Okay, so the CV that I want to use, because I need to find and determine the anchoring forces, so I want to put my CV first from here, because this is the anchoring forces that are applied here. So I want to calculate the external forces over the system here, and then because I know the velocity here, so it should also include it. So this is how I'm going to choose and select this CV. And again, the CV, the control volume, you choose it yourself, but the way that you choose it based on the given information can really make your problem easy or challenging to solve, okay? So you need to be careful of choosing the correct CV when you are solving these kind of problems, based on the information that you have, okay? So as you see, we have theta here, and the final solution should also depend on the theta. And so I'm gonna choose the CV as like this. Okay. So this is a fixed CV, a fixed control volume. This is what we call a control volume or fixed CV in a space. And now let me draw the coordinate system. So this is the coordinate system that I need to have. So this is X in the X direction, and this is in the vertical direction, which I call it Z. And so the forces that act on this system are on this vane that need to be, these anchoring forces that need to hold the vane are, one is the FAX in the horizontal direction. So it's gonna be FAX. And the other one is the vertical force, right? FAZ. I call it FAZ. Okay, so I want to find these forces, these anchoring forces. Okay. So the first thing I do is I have to write a linear momentum equation. So I write this momentum equation first in the X direction. So linear momentum equation in X direction. Okay. So I can write the velocity vector in two directions. One in the X direction, I call it UI, and this is the unit vector I here. And the other one is K, which is in the Z direction, plus WK. Okay, so I can just decompose the velocity vector into these two directions. And then I want to write this linear momentum equation, okay? So the first term is, let me just copy that here. Then we have the second term, which is the control surface one. Equals to the sum of the forces in the x direction, okay? So this equals to the sum of the forces in the x direction. So let me, instead, because this is in the x direction, I can just write u here, right? I want to first write in the x direction, as you see here. And so the other term, I can also write u, because this is in the x direction, okay? And this one, we shouldn't write it because this is the inner product over the control surface, okay? So that's not like that. And then because here the flow is steady, it's not changing in time, right? We don't see it changing in time. It's a steady flow. V1 is just 10 meters per second. And so nothing is going to change inside this control volume in time. So this term is going to be 0. Because we have steady flow. So in general, if you have a steady flow, this term is going to be 0. If you don't have any time variations, which is mostly the case in this course at least, this term is going to be 0. Only if you have time variations in a fluid, for example, they say to you that V1 is a function of time, like sine of time, right? So it's changing like sinusoidally, then this term is not going to be 0, right? So you need to account for this term as well. So this leads to the integral over the control surface of u rho v dot n dA, which equals to what? So in the x direction, so the first one, this is gonna be the integral over the control surface where the fluid exists, okay? So where the fluid exists here in my control surfaces, so the control surface is this gray dashed line that I've drawn, right? So where the fluid exists here in the on the control surface is gonna be these two green places that I have kind of pointed here. So, and the other thing is, as you see, the fluid is coming into the control volume here. So the sign of this term is going to be negative, and for this one, it's going out of the control volume. So the sign of that is going to be positive, or in a mathematical way, because the n, the normal vector here, if I want to show the normal vector is gonna be, let me show it with another color. The normal vector is out towards, always towards out of the control volume. So v2 dot n here is going to be positive, so this term is going to be positive here. This term is going to be positive here, but v1 dot n is negative. They are on the opposite direction, so this term is going to be negative here. So this is the mathematical representation of that, but the physical way and simpler way, if you want to remember, is that because v1 is going inside the control volume, its sign should be negative, and v2, because it's going out of the control volume, its sign should be what? It should be positive, okay? So this term is gonna be U2, U at 2, which is this section, times rho A at 2, section 2, times V at 2. This is a positive. And then the negative one is going to be minus U at 1, rho A1, V1 equals to the sum of the forces in the x direction. Okay? So this is going to be the integral over the control surface for this simple problem. Because V is also constant, we can just take along the control surface here. We can just take it out of the integral and just simply write A1 and A2 times V1 and V2. Okay? So now let's look at the linear momentum in z direction. This is the second equation that we need to write down. So similarly, what we are going to get is, now I have, again, for the z direction, it's again goes out of the domain. So this goes out of the domain. This is the z direction. And I know that the W1 is 0 in the z direction, but I'm going to still write it down. And similarly, we're going to get a similar equation. Okay, so it's going to be W2 rho A2 V2 minus W1 rho A1 V1, okay, equals to sigma Fy. Okay. So W2 rho A2 V2 minus W1 rho A1 V1 equals to sigma Y. Okay. So at section 1, let me put this down. So at section 1, we know that U1 is given to us in the problem. What is it? U1 is given, I think, in the problem, which is V1 equals to 10 meters per second, right? Because U1 here, V1 is all horizontal, right? It doesn't have any vertical, so W1 is going to be 0. So U1 equals to V1 equals to 10 meters per second, and W1, the vertical component of velocity at section 1, is 0. At section 2, so at section 2 now we have to find U2 and W2 based on V2, right? So you can simply say that U2 at section 2 should be V2 times cosine theta, right? And W2 should be V2 times sine theta, right? So this is something we can simply say. Okay. And the other thing is, I want to now relate V2 with V1. We know V1, but we don't know V2. And so we have to kind of find V2 in order to be able to close this system of equations, right? So how can I do that? So we have to add another equation. The problem states that we can neglect gravity and viscose forces, okay? So what does this remind to you? If viscose forces and viscose effects are negligible, that means we can use Bernoulli equation, okay? And because gravity effects are also negligible, what does that mean to you? When the gravity effects are negligible, that means that I can assume that Z1 is almost equal to Z2. Right? That is what the problem is actually telling us. So I can use gravity effects are negligible. Gravity effects negligible. That means that Z1 is almost equal to Z2. And then we use Bernoulli. Use Bernoulli. So if I use Bernoulli between section 1 and 2, P1 plus V1 squared over 2G plus Z1 equals to P2 plus V2 squared over 2G plus Z2, okay? And because the gravity effects are negligible, these two terms are going to cancel out. Z1 almost equals to Z2. And also, if you look at here, P1 at this point, it's at the vicinity of the atmosphere, so the pressure equals to the atmospheric pressure, right? And the same thing here. So this is going to be P naught, and this also equals to P naught, the atmospheric pressure. And so these two are going to also cancel out. And so this means that, interestingly, V1 should be equal to V2 from Bernoulli, because the viscosity effects are use Bernoulli because viscous effects are negligible. And because gravity effects are negligible, we can assume Z1 is almost equal to Z2. And so this will give us that V1 should be equal to V2. And so I can write that U2 should be, because it equals to V2 cosine theta, it also equals to V2 cosine theta equals to V1 cosine theta. And W2 equals to V2 sine theta. And because V2 equals to V1, it equals to V1 sine theta. Okay. So let me add another page. So now I want to substitute this into my equations here. So I have these equations. Let me see, what are my equations? This is equation 1. Equation 1. And this is equation 2. Okay, so substitute in 1 and 2, and we are going to get this. So the first equation is V1 cosine the x equation. So it's going to be, we are going to have U2, which equals to V1, right? U1, U1, which equals to V1. And then also we have U2, which equals to V1 cosine theta, right? So it's just, if you just substitute that, we are going to get V1 cosine theta, which is U2 times rho A2 V1 minus, instead of V2, I also write V1. So V1 rho A1 V1 equals to the sum of the forces acting on the control volume, which is going to be FAX, right? There is no other force here that you see. It's just the anchoring forces there. And the other equation is V1 sine theta, which is going to be W2, right? Times rho A2 V1 minus, and then the other equation is W1, which is going to be 0, right? Because of this. Just compare these two. So minus 0 times rho A1 V1 equals to FAZ. So the anchoring force in the x direction is gonna be, let me write it down here. FAX is gonna be minus rho A1 V1 square plus rho A1 V1 square cosine theta, which equals to minus rho A1 V1 square 1 minus cosine theta. And FAZ equals to rho A1 V1 square sine theta. Okay, so now we have all these, and now we have to just plug into the numbers. So FAX is equal to the rho. If it is water, it's going to be minus 1000. The rho, the density is kilogram per meter cube. And then A1 is given in the problem as 0.01 meter square. So it's gonna be 0.01 meter square times V1 square, which is given as 10 meter per second. So 10 meter per second square times 1 minus cosine theta. And if you calculate it, you're going to get minus 101 minus cosine theta Newton. Okay. And FAZ is going to be, if you plug into the numbers here, it's going to be 1000 kilogram per meter cube times 0.01 meter square 10 meter per second square, which is V1 square, times sine theta. If you calculate it, this is going to give us 100 sine theta Newton. Okay. So if your theta is 0, what's going to happen? If your theta is 0, then this means that you have just this horizontal vein, and then you just have water that is going over that, okay? And because we don't have any viscosity, both of the forces should be 0, right? There is no force that is acting on this vein because we don't have any viscosity, okay? So if you calculate it here, sine theta is going to be 0, and cosine theta is going to be, cosine 0 is 1, so this term is going to be also 0. So this shows that this formula is correct, okay? We can also investigate another condition. So if your theta, the maximum force that the maximum vertical force that this vein can handle it should handle is 100 Newton, right? And that is when we have a vertical plane here. So let me show. If you have a vertical, the theta is 90 degrees. So if theta is 90 degrees and your vein is something like this, and then you shoot water, from here, and then it goes like this, okay? So theta is gonna be 90 degrees here. So let me see. Yeah, theta is gonna be 90 degrees. And so your force, the vertical force, is going to be 100 Newton, because this is going to be 1. And this is going to be minus, this is going to be 0. So this is going to be also have minus 100 Newton in the x direction, okay? So this is how you can calculate the vertical forces and horizontal forces acting on on structures using the linear momentum theory. So it's pretty simple. If you have to first, the thing that you need to do is you need to first select a control volume. That's the first thing you need to do. That, or the best control volume that you have the information from the problem. Okay, and then draw the free body diagram of your problem, and after that, show the forces, draw the forces, draw the control volume, the velocities, all the things, and then write the linear momentum equation. And because in most of the problem you have a steady problem, the first term of the linear momentum equation is going to be 0. So we only need to calculate the momentum through the control surfaces, okay, which equals to the sum of the acting forces, okay. And this integral becomes very simple in these problems, because if you assume that velocity is constant, it's not changing in the control volume along that control surfaces, and so you only consider places where you have these fluid, which are these two surfaces, and write the whole integral for those two places, which kind of reduce it to this simple formula for this problem. And you write this in x direction and z direction, so you have to decompose your problem in if it has multiple directions. You write the linear momentum equation in x and z direction, and then you can use, this is the z direction, and then you can use the given problem, given information in the problem. And if you don't have any, if you have another unknown in the problem, you should look at the kind of statement of the problem, and then use, for example, Bernoulli equation if the viscosity effects are negligible. And because the gravity effects are also negligible, that means Z1 is also almost equal to Z2. And so this means V1 almost equals to V2, okay? And this is because A2 is not given to us. But even if A2 was given to us, here, if A2 was given, let me show it again. So if A2 was given to us, then we could also write the continuity equation, right? So we could write V1A1 equals to V2A2. And because we had everything and the only unknown here was V2, and we could find V2. Right? But because A2 was not given to us, and the only information that we had was about the gravity and viscous forces are negligible, so we can use, and we should use, Bernoulli equation. So we use Bernoulli equation, and with those given info of the problem, and then we just plugged back all these numbers that we had, and we were able to find the FAX, the horizontal force that acts on this vein, and also the vertical force that acts on this vein, and these are the forces that are needed to kind of keep the whole vein stationary. Okay, so in the next session I'm gonna solve another example for calculating the hydrostatic forces on kind of structures or pipes.